For our last algorithm in the course, we are going to look at scheduling problems. First, we're going to discuss scheduling problems generally, what the issues are and what sort of things we're going to try to solve. And then we're going to look at one very particular type of scheduling problem and learn about how to solve that one, and we'll do an example. So imagine that you're in charge of making sure some set of tasks needs to be completed and you want to do it as efficiently as possible. So we're going to think about what types of issues that you might have to address depending on the problem. How many people are you allowed to assign to work on the tasks? How much flexibility do you have to move people between tasks? How much time does each task take? Does that amount of time that each task take depending on the tasks that come before it or come after it? Do some of the tasks have to wait for other tasks to be completed before starting it? For instance, if you're trying to get a house ready for someone to live in, you can't paint the house before you build it, right? So you have to do it in a certain order. And what we're going to do is we're going to look at one particular type of scheduling problem. So here are the constraints of our scheduling problem. First of all, you're just going to have one person that completes all the tasks. For a given task, it is possible that you have to do one or more other tasks before starting that task. And not only that, but the order that you do the task is going to depend on how much time it takes each task to be completed. So the time required for a given task may depend on what tasks had been completed before it. Our goal is to minimize the amount of time it takes to complete the tasks. And what we're going to do to help us solve this problem is we are going to model it using a weighted digraph and then use some of our algorithms to find the best order possible. So the way we're going to do it is vertices are the different sets of tasks that we can complete at a given time. Now you may think that you can complete any given set of tasks at a given time. But because of the constraints on our problems, there may be some subsets that are left out. If we have two sets of tasks, say S is one set of tasks and T is another set of tasks, then when S has an arrow pointing to T, that means we can complete one task to get from S to T. So S contains a certain amount of tasks, T contains those same tasks plus one more, and that one more task can be completed from being at set S to getting to set T. And finally, the weight of the arc is the amount of time it takes to complete the one task that takes us from S to T. So here's an example that we're going to look at. We have 4 tasks that we have to complete, and I very unimaginatively call them task A, task B, task C, and task D. Here are our constraints. First of all, no matter how we do the task, A has to come before C. We can't do C without having done A first, and we have to do task B before we do task D. And other than those 2 constraints, we can do the tasks in any order that we like. So we have, for task A and task B, we have some choices. So if task A is done before task B, here's how the time that it takes to do those tasks works out. It'll take A 6 minutes, it'll take B 4 minutes. And if we do them in the other order, doing task B first before task A takes 8 minutes, task B takes 3 minutes. If we do C before D, then C takes 5 minutes and D will take 7 minutes. If we do C and D in the other order, C will take 4 minutes and D will take 8 minutes. So what are our vertices going to be? Well, let's start from the smallest vertices to the largest one. What I mean by smallest and largest, the ones that contain the least number of tasks to the ones that contain the most. So the least number of tasks that we can do, well, that's at the beginning when we haven't done anything. So that's going to be the empty set, right? Now, getting from the empty set and going to the next task, we can do one of 2 tasks. We can either do task A, or we can do task B. We can't start with task C because A has to come before it, and we can't start with task D because B has to come before that. Now, once we've done task A or task B, or let's say we've done task A, We could do task A and then task B, and that's fine, or we can do task B and then task A. So A and B are two tasks that we can do for having our only two tasks done at that point. Now, if we do task A, we can do task C. We can't do task D after task A because D needs B before it can be done. And similarly, after we do B, we can do D. Now, if we look for putting a third task into one of those, we can have A, B, C, which can be achieved at least two ways. We can do A, B first and then C, or we can do A, C first and then do B. In any case, we can have A, B, C. We can also have A, B, D. Similarly, we can do A, B first and then D, or B, D first and then A. And then after those two, after we either get to A, B, C or A, B, D, the last one that we can do is A, B, C, D. And notice that some of the subsets are missing. For instance, we don't have B, C, D because that one is impossible to get because you can't do C before you do A. All right, so here's just a list of our constraints because, there's a lot to keep track of and I want to make sure that you can see them as we do them. Let's go ahead and see what our directed graph is going to look like. So we're going to start with the empty set over here on the left. And remember, we can go from the empty set to either A or to B. We can go from A to either AC or AB. We can go from B to either AB or BD. Now we can go from AC to ABC if we wanted to, right? Because we can't go to D because we have to do B first. And we can also go from AB to AC. And also from AB we can go to ABD. And then next we can go from BD to ABD if we like. And then the last set of arrows we get are from ABC and ABD to our final destination, A, B, C, and D. And so that's our directed graph, not worrying yet about the weights of our arcs. All right, so far so good. Now let's see if we can figure out what kind of numbers to put on these things. Well, we're going to put a 6 between the empty set and A because A is coming before C, or I'm sorry, A is coming before B in that one, which means that A takes 6 minutes. And similarly, if we go from empty set to B, B is now coming before A, so B takes 3 minutes. So if we go from A to AB, now A is coming before B, and we've done B in that one, so B takes 4 minutes. And if we go from B to AB, that means B comes before A. We're doing A, that's going to take 8 minutes. And then our next one here, we go from A to AC up there. C is coming before D, and that means C is going to take 5 minutes. And then down here, we go from B to BD. D is coming before C. That means D is going to take 8 minutes. And then we sort of go similarly for all the other arcs. I'll go ahead and fill those in. You can check those out yourself to make sure I did the numbers correctly. But there is our weighted directed graph for our that models our tasks. All right, so I want to summarize some of the information that we have there. When we actually do the task, remember, we're starting having done nothing. So we're starting at the empty set. And we're finishing having done everything. So we want to finish at the set that contains all of our tasks, A, B, C, and D. We want to get from start to finish as soon as possible, which means that we want the shortest path starting at no jobs done at empty set to all the jobs done at A, B, C, and D. And if that sounds familiar, yeah, we did that with Dijkstra's algorithms. So what I want to do is find the shortest path. Let's see if we can use Dijkstra. So I want to go ahead and do that relatively quickly because we've done Dijkstra before. So we're going to start at the empty set, which is distance 0 from itself. If we look out to both the places that the empty set goes, we can either go to A or to B. B is the shortest one, so that gets the rectangle, which means that's its permanent label, 3. And the A we have circled to say, well, we got 6 right now. Let's see if we can do better. Now, if we extend from B in both those directions, we get 11 at AB, we get 11 at BD, and now the shortest one is going to be A, so we get a rectangle around A to make it permanent. That one has a label of 6. Now, we can't extend from B anymore, but we can extend from A. That goes out to AC, that gives us a weight of 11, and going from A to AB now gives us a weight of 10 instead of 11 on AB. And so our shortest one now is going to be AB, which has a label 10. Now, the only one we have left to extend from is that AB, which we can extend out in two directions, right? ABC gives us a shortest distance of 15. ABD gives us a shortest distance of 18 for now, right? So now our lowest label is 11. That's AC and BD. So those become permanent. Now when we extend from those, now from AC to ABC, we can make that a little bit shorter, make that 14 instead of 15. And that one becomes a permanent as well. And then we fill out the other ones similarly. And see, let's see. So here's what our directed graph looks like. What kind of conclusions can we make? Well, we know that our minimum time is 21 minutes because we found the minimum distance going from empty set to ABCD to be 21. That's the label that we got. Now, if we want to order the task, remember it's often easiest to order our task from our last to first, right? So if we look at the 21, we notice that 21 minus 4 is 17, not 18, so that's not the way we want to go. So we go from ABCD to ABC, which means that our last one that we do is going to be D. Now, notice that 14 minus 5 is 9 and not 10, so we don't want to go to AB. 14 minus 3 is 11. We want to go to AC, which means our second to the last task is going to be B. Now, from AC to A, 11 minus 5 is 6. That works out. We go from AC to A. That means we do C as our third to the last, or our second task. And then our last one's going to be from A to 0. 6 minus 6 is 0. That works out. And our first task is A. So minimum time is 21 minutes. We do the tasks in order A, C, B, and D. So I got another problem for you to work on in scheduling problems. That's the name of the PDF file included with this video.